You're looking to really understand something complex, right? Get to the core of it, but without feeling like you're wading through a textbook.
Yeah, exactly. No jargon overload.
That's what we aim for here.
And today, we're diving into something that, well, it might seem routine on the surface, but it's actually incredibly detailed: engine overhauls.
Ah, yes. More than just a quick fix.
Oh, much more. It's this whole comprehensive journey. You're assessing, repairing, reconditioning, basically ensuring these powerhouses are good to go for, many more hours.
Exactly. And we've got some great material to dig into, specifically some excerpts from Chapter 10, Engine Maintenance and Operation.pdf.
Good stuff.
Think of this as your fast track to understanding what really matters when you revitalize an aircraft engine. Piston engines, turbines, the whole lot.
Our mission, if you will.
Yeah, let's unpack the essentials, highlight the really crucial bits, and maybe spark a few aha moments for everyone listening. Okay, let's get into it.
Right. Let's start with the piston engines, the reciprocating ones. A really key concept is time before overhaul, TBO.
TBO, okay.
So the manufacturers, they set a lifespan, an expected number of hours the engine should run before it needs a major overhaul.
Like a best before date, but for flight hours?
Sort of, yeah. The source gives an example.
Yeah.
An engine designed for 2,000 hours, if it's flown 500, you've got 1,500 left on that clock, theoretically.
And going past that TBO, that's risky.
Definitely increases the risk. Internal parts wear down, clearances change. You go beyond safe limits. So that TBO, it's a really critical benchmark for safety, for airworthiness. It's about respecting the engineered limits.
Got it. So it's not arbitrary. It's tied directly to keeping things safe and legal, essentially, making sure everything inside is still within spec.
Precisely. And to make sure an overhauled engine is just as airworthy as a new one, there's this detailed 10-step process for a complete overhaul.
10 steps. Sounds thorough.
It covers everything: receiving it, taking it apart, all the inspections, repair, reassembly, testing, the works. And the source really emphasizes those inspection phases. Visual, structural, dimensional. They're absolutely key.
Like a deep investigation into the engine's health.
Exactly like that. A detective job almost.
So those inspections. You mentioned visual first. What's the deal there?
Okay, what's interesting is the text stresses doing this before you clean anything.
Before cleaning. Why is that?
Because any loose metal bits, flakes, particles, they can actually point to an internal failure. So that first look, that careful visual scan, can sometimes tell you right away if a part is shot. Saves time later.
Makes sense. Spot the obvious problems first. And the source uses a lot of specific terms for defects, right? Abrasion, brinelling. Sounds like a whole different language.
It kind of is. Each term describes a specific kind of wear or damage and often hints at the cause.
Right.
Like corrosion, that's loss of metal from chemical action, basically rust.
Okay.
But then you have something like galling. That's more severe metal actually transferring between parts. Usually means high friction, not enough oil. Yeah. And what's really important to grasp is even if a part measures okay, like it's still within the allowed clearance, it might get rejected just based on these visual signs if it looks like it's heading for failure.
So a scratch might be tiny, technically within limits, but if it's in a bad spot or looks like it could grow, it's out.
Exactly. The text points out specific areas needing extra scrutiny inside piston pins, those curved bits on the crankshaft called fillets, thrust bearing races. It even says pitting in those areas, if you can't polish it out, means rejection.
Wow.
Same for bolts and plugs. Minor marks might be okay to dress out, but anything significant, replace it. Oh, and here's a practical tip. Clean valve guides before inspecting. Carb buildup can hide tiny pits that could cause valves to stick later.
You really need a trained eye for this stuff. So much detail. What about the other inspections, structural and dimensional?
Right, so structural goes deeper. That's where non-destructive testing, NDT, comes in. Finding hidden flaws.
NDT.
For iron parts, forest stuff, they use magnetic particle inspection. It's like, imagine sprinkling iron filings, and they reveal hidden cracks under a magnetic field.
Cool.
For non-magnetic stuff like aluminum, there's dye penetrant. A colored dye seeps into surface cracks, makes them visible, often under UV light.
Okay.
Then you've got eddy current testing, detects surface and even slightly subsurface issues. Can even tell you about the heat treatment without stripping coatings. And then ultrasonic and X-ray, using sound waves or radiation to look inside. Different ways to find internal problems.
It's like having X-ray specs for engine parts.
Pretty much. It ensures nothing invisible gets missed. After the visual, NDT gives you that deeper look.
Okay, so visual, then structural with NDT. What's dimensional inspection? Just measuring things.
Basically, yes, but with extreme precision. comparing every critical part to the manufacturer's specs, the original dimensions, and the maximum allowable wear.
Like for cylinder barrels.
Exactly. They measure taper, that's the change in diameter from top to bottom, out of roundness.
Yeah.
The actual bore diameter, measured at several points.
Right.
The text mentions cylinder choke. That's where the very top is made slightly smaller on purpose.
Why is that?
It compensates for heat expansion and wear when the engine's running hot, helps maintain a good seal. They also look for steps or ridges inside, worn in by the piston rings. Too much of a ridge, and it can wreck new rings.
And checking the piston skirt fit must be vital too, for sealing.
Absolute critical. Prevents oil bypassing the rings, and these checks extend everywhere. Rocker arms, shafts, looking for wear, cracks, blocked oil passages. Crankshaft straightness is checked with bead locks, and a dial indicator super sensitive.
Can they straighten a bent crankshaft?
Nope. Text says bent crankshafts shouldn't be straightened. You measure the journal diameters with the micrometers too.
Yeah.
It's all about verifying everything is still within its operational window.
Okay, so after all that intense inspection,
Yeah.
what happens to parts that fail?
That leads to the repair and replacement phase. Failed parts, discarded, unrepairable, gone.
Makes sense.
Minor stuff, like small nicks or burrs, sometimes you can carefully smooth them out with fine abrasives. Warped flanges might be rubbed flat against special plate with abrasive paste.
Lapping, right.
Even damaged threads can sometimes be repaired. But, and this is important, the source is clear, welding on highly stressed parts usually needs specific manufacturer approval. You don't mess with structural integrity.
Definitely not something you'd want to freestyle. What about pistons and valves? Often replaced.
Pistons, yeah, the text says they're often just replaced during a major overhaul. It could be cheaper than the labor to meticulously clean and inspect them for tiny flaws.
Right.
Piston pins get checked closely to scoring, cracks, bends, often using magnetic particle. Valve springs checked for wobble, cracks, stretching, proper spring compression. Even tiny things like spark plug inserts are checked for tight fit and good threads.
And then the valve reconditioning.
Right.
Refacing seats, grinding valves. Sounds like precision machining.
It really is. Those valve seats in the head, they get refaced to be perfectly true, the right size, and exactly concentric with the valve guide. They often use wet grinders for steel seats, keeps things cool, better finish.
Different grinding stones, too.
Yep, sequential grades. Rough stones for shaping, finishing stones for accuracy, polishing stones for the final surface. Then they check the seat size and trueness. Prussian blue dye helps visualize the contact pattern, or sometimes light lapping. May need special grinding to narrow the seat contact area just right.
And the valves themselves get ground to match.
Exactly. On a wet valve grinder usually. First, true the grinding stone itself, then set the machine to the valve's specific angle, 30 or 45 degrees, typically. Light cuts are key for a smooth finish.
You mentioned checking the valve margin?
Right, the edge thickness. Can't let it get too thin, like a feather edge. That could cause problems, like pre-ignition. They might also resurface the stem tip for proper contact.
And valve lapping is the final seal.
That's the one. Find abrasive compound between the valve face and feet. Gentle rotation creates this perfect matte gray contact band. Then you leak test it, usually with solvent like kerosene. No leaks, good seal. The text even shows pictures of bad lapping patterns and what causes them.
Incredible detail just for the cylinder head. What if the main cylinder barrel is too worn?
Often they can be reground to standard oversizes. You need to know the original size to calculate the correct oversize. And the surface finish inside is crucial, measured in micro-inch RMS. Different engines need different finishes.
How do they grind or hone it?
Cylinder grinding uses a rotating stone moving through the bore. Some machines can do that choked bore we mentioned. Honing comes after, for the final finish. Burnishing gives a smooth surface, micromatic honing corrects distortions, and deglazing creates a crosshatch pattern, helps new rings seat properly.
Okay, so parts are inspected, fixed or replaced, reconditioned, then reassembly.
Reassembly, yes. And cleanliness is paramount here. Organization, too. Using the exact right hardware from the parts catalogs and manuals, pre-lubricating everything, following the manufacturer's procedures to the letter, torque values, safety wire, locking nuts, all critical.
And once it's back together, you don't just fire it up. There's testing.
Absolutely. On a test stand, or maybe in the aircraft, it's got two main jobs. Letting the new piston rings run in, seat against the cylinder walls, and letting the bearings burnish, wear in just right. Plus, you gather performance data.
Using all those cockpit instruments.
Exactly. The text details them. Oil pressure, oil temp with minimums, desired ranges, maximums marked, fuel flow meter, manifold pressure gauge showing intake pressure, takeoff limits, tachometer for RPM with ranges, Cylinder head temp gauge?
Right, the CHT gauge, often with different arcs for auto-lean and auto-rich mixtures.
Yes, that's where you see that interesting inverse relationship. In auto-lean, leaning, the mixture actually cools the CHT. Seems backward, but it's key for efficient cruise flight. Pilots use that.
That's definitely one of those aha things, so testing involves checking all this.
And more. Ground checks magnetos, checking for the RPM drop. Propeller controls, usually full low pitch, idle speed and idle mixture checks. The manifold pressure reading at a given RPM can even hint at cylinder health.
How so?
While higher than expected, MAP might mean a dead cylinder or late ignition timing. Lower might mean timing's too advanced. The source also covers startup, shutdown, and common problems.
Like detonation and pre-ignition.
Yep. Detonation is that uncontrolled explosion of the remaining fuel-air mix. Pre-ignition is when it lights off before the spark plug fires, usually caused by excessive heat or compression for detonation or hot spots for pre-ignition.
And backfiring. After firing.
Backfiring is an explosion in the intake or exhaust. After firing is unburnt fuel igniting in the exhaust, often linked to wrong fuel mixtures, ignition issues, stuff like that.
It's amazing how things like valve clearance affect the mixture and how smoothly it runs.
Totally. The text touches on troubleshooting systematically. Diagnostics like checking for valve blow-by, doing cylinder compression tests.
Compression tests, right, to check the seal.
Exactly. Differential pressure tests, too.
Yeah.
You listen for escaping air exhaust, intake, breather, helps pinpoint if it's a valve or rings leaking.
And if a cylinder needs replacing.
The source covers that. Proper piston orientation, staggering the ring gaps, torquing the hold-down nuts correctly, vital steps. Finally, there's the cold cylinder check, identifies cylinders not firing right during operation.
Okay, that's a really deep look at reciprocating engines. Let's switch gears. Turbines, jet engines. Overhaul must be quite different there.
Very different in some ways, yes. And turbine maintenance varies a lot between engine types, so the manufacturer's manual is absolute gospel. But generally, you think of it in two main parts: the cold section and the hot section.
Cold and hot sections, okay.
And a huge concern for turbines, maybe the biggest headache, is foreign object damage, FOD.
FOD. Stuff getting sucked in.
Exactly. Even small debris can wreck compressor blades, hurt efficiency, cause massive damage downstream. So preventing FOD, careful work habits, inlet inspections, is paramount. It's a different kind of vulnerability compared to the internal wear focus in piston engines.
Makes sense. So inspecting the compressor, what are they looking for?
Damage to the blades, nicks, dents, cracks, corrosion. This applies to both axial flow types, with rows of blades, and centrifugal ones that spin air outwards. There are strict limits for repair. Minor nicks might be carefully stoned or blended smooth.
But cracks.
Zero tolerance. Absolutely no cracks allowed on compressor blades. The stresses are just too immense. A tiny crack could lead to catastrophic failure at speed.
Wow. So any crack means replacement. Really highlights the forces involved. What about the hot section, combustion area?
They're looking for signs of overheating hotspots, fuel or air leaks, any distortion or warping, cracks, wear. In salty or corrosive air, they might do regular turbine washes to clean things out.
And the actual turbine part, after combustion.
Meticulous inspection there too. Turbine discs checked for cracks, pitting. Turbine blades looking for stress rupture cracks, which happen under high heat and load. Deformation, wear on the blade tips or shrouds. The inlet guide vanes too.
I remember reading something about balancing moment weight.
Yes, that's fascinating. When blades are replaced, they aren't just stuck in anywhere. Each blade has a specific moment weight, and they have to be installed in a sequence to keep the whole rotating assembly perfectly balanced. Incredible precision.
That really is next-level engineering. And the exhaust section.
Check for heat cracking, warping, buckling, any hotspots indicating issues upstream. The source then briefly mentions engine ratings, flat rating, wet thrust, older concepts mostly, and then the instruments.
Right, different gauges in a jet cockpit, EPR, EG2.
Correct. EPR engine pressure ratio, that's the key thrust indicator for turbofans. Ratio of turbine exit pressure to compressor inlet pressure. Turboprops use torque meters, measuring shaft power. Tachometers show percent RPM. And EGT exhaust gas temperature is vital for monitoring turbine health and operating conditions.
How do they check takeoff thrust?
Using the EPR gauge, comparing it to thrust, setting curves for that engine, and factoring in ambient conditions, temperature, pressure, altitude, they affect performance significantly.
And operational things, like needing a cool-down period.
Yep. After high-power runs, you need a cooling period before shutdown. Prevents the turbine wheels seizing as they cool and contract unevenly. Also, there's a specific waiting time after shutdown for an accurate oil level check.
Makes sense. Troubleshooting turbines.
Similar logic, systematic process based on understanding the systems. Turboprops are mentioned too, similar to jets, but with the propeller and its controls, and the torque meter is key.
And that jet cool analyzer thing.
Ah, yeah, an older piece of test gear used for calibrating EGT and RPM systems on the ground. Could check the circuits, help find bad thermocouples, indicator errors, shorts, things like that. Compare aircraft attached to the analyzer's reading.
So whether it's pistons doing their dance or turbines spinning at incredible speeds, an overhaul is, well, it's a massive undertaking. Way more than just fixing broken bits.
Absolutely. It's a deep, deep dive into the engine's core. We've seen the initial visual clues, the NDT tech finding hidden flaws, the micron-level measurements.
Yeah, and those surprising details, like the CHT behavior in auto lean or the turbine blade moment weight balancing. It really shows the complexity.
It does. And it all comes back to meticulous inspection, following the manufacturer's specs to the letter. That's what ensures airworthiness, safety.
Non-negotiable.
Right. When you think about all these steps for both engine types, it really highlights the amazing engineering involved and, frankly, the incredible skill of the technicians who do this work.
Yeah.
Keeping these complex machines reliable.
It really does. So thinking about all this incredible detail and precision, what does it tell us? Not just about how vital maintenance is or the skill involved, but maybe what other complex systems we rely on every day might have these same fascinating depths if we look closer.
That's a great thought to leave people with. What else looks simple on the surface but is incredibly intricate underneath? Worth pondering.